Now we will solve the problem with extended charge. We'll have x and y. I will have now charge q that is uniformly spread along x from x minus a to x plus a. Charge q is uniformly spread along x-axis from x minus a to x plus a. And we want to find the force exerted by this charge q on charge q node. Charge q node that is located distance h from the origin along y. We want to find the force acting on q node, y charge q. Well, we know how to find the magnitude of force, between 2 point charges. According to Coulomb's law, it is coefficient k and then product of magnitudes q1, q2 divided by distance between them squared. But we do not have a point charge. We have charge q that is spread along x. So how can we apply this formula? What we need to do, we need to slice this extended charge q into infinitesimally small pieces, dq. And if I have dq, point charge, dq, then I know how to write magnitude of force between dq and q node. So what's important? This dq, infinitesimally small charge, is located at arbitrary distance x. Then we slice this rod into this dq, dq, dq everywhere, and we can integrate from minus a to a. We will integrate over the rod. So here's dq. Now I can write df, magnitude of force between dq and q node. It is coefficient k. Then magnitude of dq, magnitude of q node, and divide by distance between them squared. What is distance between them? Distance between them is this line. And I will find the length of this line using this right triangle. So this is hypotenuse, and this hypotenuse is equal to x squared plus h squared. X squared plus h squared will be distance squared, and this is magnitude of df exerted by dq. I cannot write f, I write df because I have infinitesimally small charge dq, and then I need to integrate df over this rod. So I will find my net force F as integral from minus a to a of df as a vector. Okay, so as always, what we need to do, we need to write this force in terms of components, force df. But before we start doing that, let's look at this picture again. So I have dq located right here, and look at this. I have another dq located at minus x. And if we draw forces exerted by this dq on q node, and this dq on q node, we will see that these forces will have x components equal and opposite. X components of this force will be equal and opposite. So we will immediately write that from symmetry, Fx of the net force, x component of net force, is 0. All we need to find y component of force. So let's put df here and df. I'll probably, oh, it's okay. So df and df. So x components cancel each other. Now y components, we just add them together. So basically what we can do, we can integrate from 0 to a and then multiply it by 2, because from symmetry we see that y components will be added together. What we need to do now, we need to write dfy. So dfy, y component of my df, will be equal to k dq q naught divided by distance between them squared, which is x squared plus h squared. And to find y component, I need to multiply. If we introduce, which angle we will introduce? Let's introduce this angle theta, then this angle is theta. So to find y component, I need to multiply by sine theta. Very good. So now I need to find sine theta, and I need to figure out what is dq. So let's start with dq. dq, by definition, is lambda, charge per unit length, times length, dx. Lambda is charge per unit length. Since q is uniformly spread along this line, lambda is just charge q divided by length. Charge per length, and length is 2a. So my dq is q over 2a lambda and then dx. Let's find out what is sine theta, and then we will bring everything here. So what is sine theta? I will use different color for sine theta. Let's use blue. Sine theta. Sine theta is opposite leg, which is h, and I divide it by hypotenuse, which is x squared plus h squared, square root, x squared plus h squared, square root. So now let's bring dq and sine theta back to our dfy. So I have dfy, and it is equal to k q naught divided by x squared plus h squared, but before it, let's write dq. So dq is q over 2a dx. This is dq. Then I'm right here, dq. So what is left is x squared, 1 over x squared plus h squared, and sine theta. And sine theta is h divided by square root of x squared plus h squared, which brings me to x squared plus h squared to 3/2. So now we can integrate. We expressed our dq and sine theta in terms of x. Now we can integrate. Let's do it. So what will be fy? So I have fy, y component of the resultant, is equal to integral. From symmetry, we see that we can integrate twice from 0 to a. Twice from 0 to a. Then I will write all constants first. So I have k q naught q over 2a and h. K q naught q over 2a h. Those are constants. I can bring them out of integral. And what I need to integrate will be dx over x squared plus h squared to 3/2. This is equal to, we can simplify it. Oh, let's keep it. 2k q naught qh divided by 2a, constant, and then integral dx over x squared plus c to 3/2 is stable integral. You don't need to memorize it. It will be provided on the exam if you need it. So this is equal to x divided by c, and then x squared plus c to 1/2. We will use this stable integral here. So integral dx x squared plus h squared to 3/2 will be equal to x divided by c. C is h squared. Then x squared plus c, and c in our case is h squared to 1/2. The limits of integration are from 0 to a. Now we plug in these limits. I rewrite constants. Let's simplify it. 2 and 2 cancel out. Then h and h squared. So I have k q naught q divided by a h. And then upper limit gives me a divided by a squared plus h squared to 1/2. And low limit gives me 0 because x0, low limit will give me 0. And this is our Fy component of the net force. So the resultant force acting on q naught by q will be equal to, I will write it right here. So force exerted on q naught will be equal to 0 ix. You can skip it. You don't need to write 0 as x component. And y component, let's simplify it. So here is a and here is a. Y component will be k, q naught q, divided by h, and then a squared plus h squared to 1/2. And this is y component. This is our final answer. And now let's consider one limiting case. Let's bring q naught far, far away. So I will erase dfy, and we will consider this limiting case when we have a much smaller than h. We can erase this a little bit at the end to accelerate. A is much smaller than h. Then what will happen? So q naught will be far away from this charge q, and the net force F will still have 0x component, and y component will be k q naught q divided by a is small in comparison with h, we neglect it, then h squared to 1/2 gives me h times h is h squared, and this is exactly what we expect, because when we bring q naught far away from q, q acts as a point charge. So we'll just get the force between two charges, point charges q naught and q. Q naught q divided by h squared.